So bending stress, the homework assignment looks something like this. So I'm just gonna say we have a 2x6 Doug fir. Yours is gonna be a C shape. And we're gonna put 1,000 pounds on it. And it's gonna be 2 feet from one end and 6 feet from the other end. All right, so it almost always is gonna start with a statics problem. This load for the project, you're gonna have to estimate loads. So with a bunch of stuff on it, I might weigh 170 pounds type of thing. But we'll put 1,000 pounds on a Doug fir 2x6. What we want to know is bending stress. And that's MC over I. Moment. Centroid distance from the neutral axis to the outermost fiber is C, and then inertia. So the inertia is based off of this shape. We can look that up. C is based off of this shape. You can look that up. So really the challenge with bending stress is understanding the load, which is a moment, right? So we have to do our statics first and figure out these reactions. Call this AY, this BY, and I'll get my calculator. You can do it too. You probably do it faster than me now.
We need the weight of the beam.
We're gonna neglect the weight of the beam because we have 1,000 pounds compared to a 2x6 weight, which is probably 6 pounds. If I get 750 here, that would be 250 here. Anybody else agree with that? Okay. Then what do we do? If we wanted to know, what we want to know is what is the maximum moment, right? Where on the beam is this maximum moment and how big is it? So the way we did that was, anyone remember? Shear and moment diagrams. Yeah, remember in this? This is flashbacks.
Yeah.
They get hard, but most of the time they're simple. Like this one's gonna be fairly simple. But they get complicated. Yeah. So remember, shear is this down force. It's like, is it gonna just shear off, right? So shear is all about forces. But then we can make the moment diagram from the shear diagram. That's the easiest way to do it. So the way we made the shear diagram is we literally just follow these forces. Starting at the left side, it goes up 250. And they're pounds. This is just force diagram or shear diagram. Then as you move along, if there's nothing going on, there's no distribution, there's nothing happening force-wise, that's just a horizontal line. Until you come to another force. Yep. When you come to that force, you follow that force and it's a down force. So we're gonna go down 1,000 pounds. So from 250 down to 750. Right? Follow the forces. If you've done it right, you end up back at 0. Because these are all simply supported beams, they're in equilibrium. That diagram should come back to 0. If it ever doesn't, you probably got an error in your reactions. 750. Right? So if you're going to do like a shear analysis of this beam, like, hey, will the 1,000, if this 1,000 was super close to the BY, like right over next to it, that's where we get big shear loads, right? Because that's acting like kind of like a pair of scissors, right? It's just a up, down, right next to each other. This is out quite a ways. The maximum shear is 750. We would use the 750 pounds and put it into the shear equation for shear stress, and we could calculate that. Right now, we're just trying to find bending, right? So to make the moment diagram from the shear diagram, you think about plus areas of the shear and minus areas of the shear. Plus area means that is positive slope in the moment. And positive slope is up and to the right. Negative slope is down and to the right. Okay, because we're always working from the left to the right. That's the easiest way to do it. So if I'm over here, I see positive slope and I see negative slope, right? So that means, oh, it's got to go up. This is a smaller slope. This is a larger negative slope, but it's larger, right? It's a 750 value. So the value of the slope is this diagram. So I'll make this one kind of flat, and you just kind of represent best you can. And it's going to interfere with my shear diagram, but that's okay. Right? So I made it kind of at a moderate slope, and then it's going to go negative, and it's steeper, which makes sense, right? Because it's also going to return to 0. So you kind of read the shear diagram, you're reading slope of the moment diagram. So it goes positive, 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 and then it goes negative, 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 negative. Comes back to 0.
Okay, if you've got a distributed load,
Yep,
then in the shear diagram,
yep,
it's angled. The moment becomes like a parabola.
yeah,
looking-
parabolic
okay,
curve,
what I
that's
was-
exactly
okay.
right. Yep,
We don't just convert the distributed to a single force.
nope, not in strengths. We leave it as a distribution. So if there's a distribution here on our beam, this is what Amy's asking, right? And this is a down distribution. So then in the shear diagram, there's probably a reaction going up and a reaction going up, right? So it sees the reaction first and it goes up. And then it comes down at some slope, straight line. Make it a curve. Oh, man. Right, so this is a different problem if there was a distribution. So in the shear, it comes down and then maybe goes flat. If this is going back up, then it must actually cross. So here, I'll put a down force. Then that'll kick it down to here, then it comes across, and then it comes back up. Okay?
Mhm.
So this may cross, it may not cross. You have to do the numbers to figure out whether it crosses. So that's a shear. So then in the moment, we do the same thing. We think about it the same way. This is plus slope. And I think of it as big plus slope, right? So I would go like, oh, it's plus. It's kind of steep and up. Here it's what? It's still plus, but it's less. So it's like, oh, it's like this. And this, it's like this. A little less, a little less. And here it's still going up, but just very little. And if you think of that kind of in pieces, it'll give you the curve, the parabolic curve. So yeah, that's the tricky one. All right. So once you do this and you figure out, oh, where's the maximum moment? It's right here. Right here, right? That's the maximum moment. Just looking at the moment curve. How do we get that number? Because that's what I want here. Area of the shear gives you the moment. Area of the shear is what? It's 6 feet and 250 pounds. Area of a rectangle is 6 times 250. 6 feet times 250 pounds equals 1.5? No, 1,000.
1,500.
Yeah, thanks.
Let's keep talking.
1.5. I got the 1 and the 5. I just couldn't figure out the rest. Foot pounds, right? And that's a moment. That's this. And that's that. Now we can calculate bending stress. So be careful when you do it. Because you have 1,500 foot-pounds. And then this is our cross-sectional area, which is 2 by 6, that's gonna be 5.5 and 1.5, right? Yep. And so our C value is gonna be half of 5.5. Right, because the C value is from the neutral axis to the outermost fiber. C. So what's that, 2.5, 2 3/4 inches. So you have to be careful because you got feet in inches, that's got to be dealt with. And then it's over the inertia, and I would just look the inertia up for a 2 by 6. Two by 6 is an inertia of 20.8.
No units?
No
No units?
inches to the 4th,
Oh,
20.8 inches to the 4th. So for stress, we want PSI. That's the normal table unit. So really, you just have to convert the feet to inches. Leave the inches alone for C and for inches to the 4th. And then say, oh, I know there's 12 inches per foot. And then the feet cross. So it's a factor of 12 up above. Uh, 2379. 0.8 PSI. So pounds are left here. We have inches above and inches above. So inches squared above, inches to the 4th below, pounds per square inch. Okay. So the final thing would be like, is that good or bad? This is Doug Fir, right? So how much can Doug Fir take in bending stress? 'Cause this is a bending stress. Well, let's look. Values of timber. And we have an FB that would be bending in PSI, and it is 900. So yeah, how's our 2 by 6 doing? No boy, no, not good. So 1,000 pounds is not pretty and not gonna work, and that's exactly what we want to learn. Then if we really had to carry the 1,000 pounds, we'd have to adjust the area of the timber, right? It's gotta get bigger. What's it gotta be? Who knows? We can either keep guessing and checking, a little trial and error, right? Oh, 2 by 6 doesn't work. I wonder if a 4 by 6 works, and you try that. The other way to do it is to use this equation, right? You know your max, if you don't want to change the load, you know your moment, that moment's not going to change, right? C changes, so you put C in as a variable, and then you put I in as a variable, and try to reverse calculate the area required. It's a little bit hard to do because it's inches to the 4th down below, and it's just a pain. So I'm a big fan of trying a bigger piece of wood and just recalculating. So that's bending stress
Oh,
on a basic level.
For the homework,
Yeah,
pretty sure I neglected the weight of the beam.
for
did.
the,
I did that too the first time, but I caught it.
I neglected.
okay.
So for